Hi there YouTube. So in the previous video I promised that I was going to do a series of videos going into the technical details of hang glider design. So this is the first one in that series. So what I'm going to do with these next videos is I'm going to go into the details about how hang glider works, so how we can go about designing one, and then eventually how we can go about improving the design of one. So one of the things I said in the last video was that designing a hang glider is hard, and that's true because hang gliders are really a completely unique type of aircraft. They are very different in some really key ways to conventional aircraft. So to back that up a little bit, let's think about a conventional aircraft first. So you can see here we've got a picture of a glider. So the way this works is that you just have one item which does one thing really. So we want to generate lift, obviously, so we have wings, and the job of the wings is to generate as much lift as possible while generating as little drag as possible. Then we need pitch stability, so we put a horizontal stabiliser on it. We need yaw stability, so we put a fin on it. We need control in pitch, in yaw and in roll, so we put elevators, rudder and ailerons on it, so we have control surfaces. So if you're going about designing an aircraft like this, although admittedly it's a whole lot more complicated than this, but in principle, if you design a wing which is really efficient and then you put a tail plane on that which gives you enough stability, and then you add a rudder to give you enough yaw stability, and then you put control surfaces on which are sized big enough to give you the required control, then you'll have a pretty good aircraft. Now there are interactions between those things, and obviously there's a more optimization to it than that, but that's the fundamentals. Whereas if we look at a hang glider, then you've only got one surface here. So if we try and think about what this has to do, it's kind of a bit like that. So we still need all of those jobs, that all of those bits we're doing on the previous aircraft. We need to generate lift with minimum drag, we need pitch stability, we need yaw stability, and we need some roll stability, and we need control in turn and in pitch. So we're trying to do all the same things, but we're trying to do them with just one single surface. And then to add even more complication to that, that surface doesn't even stay the same shape when it's in the air. Well, obviously it has to move, to turn, to provide that control. And we've got the VG, but even beyond that, as you change the angle of attack of this wing, you're going to be changing the pressure distribution, which is changing the load on it, which is changing the shape of it. So it's a really difficult system to analyse. I mean, normal aircraft, obviously a wing bends when you put force on it, and bends and twists as you put load on it, but the amount that a hang glider wing does this by is just much more than other aircraft, and because it is a tailless flying wing type aircraft, that also adds the complexity into it. So this really is quite a complicated aircraft to try and design by any standards. So my plan is that over the next few videos I'm going to go through those aspects in a bit more detail. What I'm going to talk about today is stability, so how stability interacts with lift, because basically you need both stability and you need lift or you don't have an aircraft. So we're going to talk a bit about pitch stability today. So we'll start off by describing how it works on conventional aircraft, because that gets us on to how it works with a hang glider. Let's start off by thinking about just a simple dart. Now a dart is something which is sort of obviously aerodynamically stable. It's kind of intuitively easy to understand how it stabilises itself. If you sort of imagine something happens and it gets a little gust and the front of it comes up, the back of it goes down, well, the air's going to push on those flights and it's going to tip it back to level again. So that sort of makes sense. And obviously if it goes the other way, if it gets pushed down, then if the front goes down, the back goes up and the air is going to push the back down into line. So it's sort of easy to sort of intuitively grasp that, but then you start thinking, well, how does the dart know which end's the front and which end's the back? Well, which is really about saying, well, what's the point it rotates around? And that point is its centre of mass. So the dart is rotating and the centre of mass is very far forwards, so the dart is rotating about that point, so the flights are obviously on the back of it. So it's telling you it's not just the flights that's important, it's also the position of the centre of mass. Now, the other thing about a dart, of course, is that because that centre of mass is so far forwards, the only things that are anything like wings are on the back of it, well, it's going to keep on tipping itself further and further forwards. So although it's stable, it's never going to reach stability until it's in a vertical dive. So it doesn't generate lift. So that's the other critical thing about an aircraft, obviously, is that it has to be stable, but it has to be stable while creating lift. So now that gets us on to thinking about wings. So the wing obviously generates lift. Now, we're not going to go into the details of that for this video, maybe that's one for another one. But basically it's doing that by creating a pressure across it. So lower pressure on the top, higher pressure on the bottom. That's where the lift comes from. So you can kind of think of it like every tiny little piece of that wing is generating a little bit of force. And when you add up all of those tiny forces all together, then you get the overall force that the wing's generating, which is up the lift and also angled back a little bit as well, which is the drag component. The point that red arrow is acting through on the wing is what we call the centre of pressure of the wing. When you're designing an aircraft, one of the important things is to decide where to put the centre of gravity. So you can control that by basically where you put the heavy stuff. In hang glider, that's largely the pilot. If it was another type of aircraft, it would be fuel, engines, and so on. So we can move the centre of gravity around a little bit by changing the position of the stuff that is inside it. So let's just say, for argument's sake, that we put the balance point exactly on where that lift is being generated, because you can kind of immediately see that if you put the balance point just a little bit behind it, then the force from the weight is going to act down behind the force from the lift, so it's immediately going to do a backflip. If you put that balance point in front, then it's immediately going to go into a vertical dive. So let's just say if we put that balance point exactly balanced with where the lift is being generated, well, theoretically, if you didn't have any gusts, if this was a perfect world, if nothing happens at all, then it should just balance and your lift equals your weight and this thing will fly. But of course, we're not in a perfect world. So let's just imagine what happens if you get a little gust. So say something happens to tip the nose just a little bit up. So the wing's obviously now at a higher angle of attack. So that means two things happen. So the first is that it generates more lift overall. But the second is that because the distribution of that pressure has changed, then if you add all those little forces together, they're not acting through the same point that they were, and actually the point at which they're now acting through is further forwards, so it's now in front of where we put our balance point. So now we've got a force acting upwards in front of the force that's acting downwards, so of course we're back in this situation where the wing's going to do a backflip. And if you had a situation where the gust pushed the front down instead of up, then the opposite would happen and you'd end up going over forwards. So although if you put the centre of gravity where the centre of pressure is, you've got a static equilibrium, it balances, it's obviously not stable. So that's why we need to add something to make a wing stable. Now you can probably see where I'm going with this. So intuitively you can probably see how if we put something like the tail of that dart on behind here, that would stabilise this. It's sort of almost a bit like a weathercock on a church, that it tries to keep pointing into wind. So like that dart tries to keep pointing into the airflow, it's going to stabilise this thing out. But of course, we're thinking about this from the point of view of how do we design an aircraft, and if you're going to start to design an aircraft, you're going to have to understand it in a bit more depth than that and be able to put some numbers to it. And to do that, we need to start thinking about something called moments. So in engineering terms, a moment is a twisting action that's created by a force, and it's taken about a certain point. So the classic example of this is like a spanner on a nut or a bolt. So you've got this twisting action around the bolt, and you've got a force being applied to the end of the spanner. Now, the moment, the twisting around that nut, is it's the product, the multiplication of the distance away from that pivot and the amount of force that's being applied. So if you put more force on it, you get more twisting. If you use a longer spanner, so you have a bigger distance, you get more twisting. Now in this case, it's quite obvious where the centre, where the point is that we're measuring the moment about. It's the centre of the nut. But actually you can calculate a moment about any point that's convenient to measure it about. So for example, in this case, it might there's the centre of the nuts that we're trying to turn, but then in this example there's also the centre of the wheel, so you could also calculate the moment about the centre of the wheel, and then if you're not holding the brake on, the wheel might turn instead of the nut that you're trying to undo. So in that example, the moment about the centre of the wheel is actually bigger than the moment about the nut, because although the force is the same in both cases, I'm putting the same force down through my hand, in the case of if you're measuring or if you're calculating the moment about the nut, you're using the distance which is from the nut to my hand. If you're calculating the moment about the centre of the wheel, then the distance is bigger, it's further. So a moment only makes sense if you're thinking about it about a particular point. You calculate a moment around a point. So in this particular example, we can kind of take these points, they're physical points on the car. Your nut rotates around its shaft, the wheel rotates around its hub. If you're thinking about something like an aircraft or a wing, it's not so obvious what the point is that it rotates about. It's sort of a free body, it can move around, so where do we take our moments about? So a moment is something that you calculate. It has this sort of physical meaning that it's twisting, but it's twisting about a certain point. So you have to choose what point do I calculate my moments about. So sometimes you pick different points for different reasons. Sometimes we might take the centre of mass as being the point that we measure moments about. It's usual that we pick a point that has one of the forces acting directly through it. So if you pick the centre of mass as the point that you're measuring moments about, that makes sense because the weight is acting through that point. So that means that by definition the distance is zero, so the moment that the weight is creating is zero, which is useful. You might also pick the centre of pressure as being the point for the same reason. So your force is the lift, but the distance from that point, if you're acting through the centre of pressure, the distance is zero. So your moment that's created by the lift force in that case is zero. The problem with doing that is, as we've already said, the centre of pressure moves around according to the angle of attack. So it's really not a good idea to be considering a point which is going to be moving to try and calculate moments around. So as I say, sometimes we pick the centre of mass as being the point we measure moments around, but sometimes we can pick some other points as well. So a point that's often talked about is the aerodynamic centre of the aerofoil. So sometimes people confuse this with the centre of pressure. It's not the same thing. So the centre of pressure is the point at which you can count all of the lift as acting through. The aerodynamic centre means something different. So let's just consider if we pick a point somewhere in front of where the lift is being created, so somewhere in front of the centre of pressure. Now we calculate our moments around that point, so the moment around that point is the product, the multiplication of the amount of lift that you're creating and the distance that that lift is being created from our point, so the distance that the centre of pressure is away. Now if we imagine as we increase the angle of attack of the wing, the amount of lift you're creating gets bigger, but the centre of pressure moves forwards, so that means it's moving closer to this point that we've selected to measure our moments about, so that means the distance is getting smaller. Now for a lot of normal aerofoils that we're going to be thinking about, both of those things happen in a linear way. So the pressure, the lift increases linearly. It also moves forwards linearly. So you can see that there is one point where those two effects cancel out, and so the lift is getting greater, but the distance is getting smaller, and so actually we're keeping the moment at the same level, so the moment is constant, and that point is the aerodynamic centre. So it's the point at which the moment is constant across the range of angle attacks. Of course, when it gets close to stall and so forth, then it deviates a bit and the centre of pressure moves in a non-linear way and the lift is generated in a non-linear way, so this relationship breaks down. But for most angles of attack, this is a constant. Now, the moment isn't zero. It's important to note that the moment is down, like it's trying to tip down, because the lift is always being created behind the point that we're considering our aerodynamic centre. So it's always going to be trying to tip the wing forwards, to tip the wing nose down. For most normal wing sections, that aerodynamic centre point is usually at or close to the quarter chord point, so that's as in a quarter of the way back from the leading edge along the wing's chord line. Now, as I said earlier, part of the aircraft design process is to choose where to put the centre of gravity. So if we were to put the centre of gravity a long way forward, so in front of the aerodynamic centre, you would get something which would be technically stable, but it would be stable in the same way that pub dart is stable, i.e. it would only be stable when it's in a vertical dive and it wouldn't be generating any lift at all, so it's not an aircraft. So what we need is some way of counteracting that negative pitch moment which we have at the moment. So this is the tendency of it to pitch nose down. So we need to put something on it which makes it pitch nose up to counteract that while still being stable. So that's the purpose of the tailplane. On a conventional plane, the tailplane is on the back and it's angled down compared to the main wing, so it's pushing down on the tail, which is pushing the nose up. So the tailplane's obviously much smaller than the main wing, so obviously it generates much less aerodynamic force. But because, as we were talking about moments earlier, a moment is a force multiplied by a distance. A small force at a long distance, and the tailplane is a long way away from the centre of gravity, can be the same moment as a large force with a small distance, as in the wing. So those two moments can cancel each other out. And also then what happens is that now, if we consider our stability, so what happens if it gets, for example, a little gust that tilts the nose up, well, even if the wing is destabilising, so the wing is trying to make the nose pop up even more, the tailplane, because it's also increasing its angle of attack, it's now generating either positive lift or at least less downforce. And because that distance that it is away from the centre of gravity is so much greater than the wing, it can have a bigger turning moment than the wing has. So overall, the aircraft is now stable. So one thing you might have noticed is that in normal flight then, so if the tailplane is pushing down, that seems pretty inefficient, and yes, actually there is a penalty to be paid for that. So if you've got a tailplane that's generating downforce, then the wing obviously has to be creating that bit extra lift to overcome that, so that the total lift that's generated by the aircraft still equals its weight. So sort of having those two bits of the aircraft fighting against each other in that way, the wing generating lift, the tailplane generating downforce, that has a drag penalty, and this is called a trim drag. So it's a drag penalty that is paid for stability. So you might be wondering, well, is it possible to have both surfaces lifting? Yes, actually it is. This is how a canard design works, like the Rutan Long Easy in this photo. So the way this works, if we think back to the wing as we had it, we put the centre of gravity, so the pivot point that the aircraft's working about, far enough forwards in front of the main wing, then the main wing becomes stabilising. It's like the flights on the Dart, that it will act to stabilise the aircraft, but it's only stable when it's in a vertical dive, like the Dart would be. So in other words, it's got a nose down pitching moment. Now, if we try and counter that nose down pitching moment, instead of by pushing down on the back, but by pushing up on the front, that's what a canard type configuration, that's how that works. So if you think back to the kind of weathercock analogy, we've got the main wing now behind the pivot point, behind the centre of gravity. So it's now the main wing which is actually doing the stabilising action. The front wing, the canard, is actually destabilising, but what it's doing is adding enough lift to counteract the nose down moment that the main wing is creating. Now, of course, the main wing, which is the rear wing in this case, is bigger than the front one, so it'll naturally try to generate more lift. So, all other things being equal, we'd still have the problem that it will be nosediving. So, we need to get more lift out of that front wing, but of course, if we just do that by making it bigger, because it's in front of the centre of gravity, it's going to add destabilising effect. So we need to increase the amount of lift that the front wing is generating without making it any bigger. And the way to do that is to increase its angle of attack, so to mount it on the fuselage at a higher angle than the main wing, which is exactly what's done on any canard aircraft that's designed to be stable. Some fighter jets have canards, they're not designed to be stable, the electronics stabilises them, but for things like the Rutan designs, they'll always have the front wing set at a higher angle than the rear wing. So the front wing is generating more lift per unit area than the back wing. In other words, it's flying at a higher lift coefficient than the rear wing is. Now, we can also extend that concept onto tandem wings as well, because if you imagine, we just take this case, we increase the size of the front wing, decrease the size of the back wing until they're the same size. Consequently, we're going to have to move that centre of gravity forwards, because the front wing is going to now be generating more lift than the back wing, because not only are they the same size now, but the front one's having to generate more lift per unit area, so it's generating more lift in total, so the centre of gravity has to go forwards of halfway between the wings. And this will also be a stable aircraft, so there's examples of tandem wing aircraft too. And then if we were to sort of take this tandem wing and shrink down the tail so that it's smaller, so the rear wing is smaller than the front wing, of course we're back to our conventional aircraft, but at some point we'll get to a stage where the rear wing is a bit smaller than the front wing, or somewhat smaller than the front wing. It can still be generating lift, so your tailplane can still be a lifting surface as well as the main surface. Now, this sort of gets around that problem we had with feeling like, well, the tail's either not generating any lift, or at worst it's even generating some downforce, which seems quite inefficient. But actually, as with so much in aircraft design, when you start to get more into the details of this, you start to realise that actually those other compromises that you need to make on the canards and on the tandem wing type aircraft, you're making different compromises instead. You're not losing this performance directly by having the two surfaces effectively fighting each other, but if you're making, for example, a tandem wing, you're limiting aspect ratio, so, and the span of the total thing, because you've got to split the liftings between two wings rather than making one really efficient wing. So for conventional aircraft, the sort of the optimum really is actually a conventional tailplane, and so you try and make the main wing as efficient as it can be, which means it's as large as it can be, and then you add a tailplane to that, and you're probably aiming for the tailplane to be not lifting or pushing up or pushing down at the design condition. So for all three of those cases, the conventional, the tandem wing and the canard design, they all achieve stability in the same way. So the centre of gravity has to be far enough forwards to make it stable. So if you go back to that weathercock analogy, that's like the pivot point on the weathercock has to be far enough forwards. It needs to have enough area behind it to keep it aligned. But then also, because this is an aircraft and it's got to generate lift, it's got to be generating lift at that point. And to do that, we need the front surface, whichever one that is in the three cases, to be working harder than the back surface. So it needs to be generating more lift per unit area. It needs to be running at a higher CL. In most cases, that's achieved by angling it at a higher angle to the main wing, or to the rearwards wing, I should say. That's not quite the only way it can be done. Also, tweaking wing sections do have an effect, but changing the angle is the most powerful way to change the lift coefficient. So in almost any stable aircraft, you will always find this feature that the front surface is at a higher angle of attack to the back surface. And even some pretty extreme designs, like this 9-wing seaplane designed in the 1920s, you can see that just from this photo, you can see that front set of wings is at a higher angle of attack to the middle set of wings, which is at a higher angle of attack to the rearward set of wings. So we have this changing angle between the sets of wings. This is often called longitudinal dihedral. So I've explained how conventional aircraft can generate pitch stability while still generating lift, also how tandem wings and canards do the same. What I've not described yet is how that works when you only have one wing surface. So rather than having the relative angle between your two surfaces, how do we do it when we only have a flying wing? Which of course is what we're getting to with hang gliders. That's the subject for the next video, but the clue is it still involves longitudinal dihedral. Also, please don't forget that I do have a Patreon page running, so that's basically there to fund the actual work of doing the hang gliding development, but also to give some support for making videos like this as well. So please go on that page and if you can, help to support this work.